I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss one very important theorem, that is Bloch Theorem. We have started with module 2, that is Introduction to Solids and Semiconductors. And in the last lecture we have discussed very clearly about the introduction to free electron theory. So we will be using and referring to the free electron theory while discussing the Bloch theorem today. So to understand Bloch theorem, it is very important to have a clarity on free electron theory. Some of you who have not seen the video, you can refer to the video and see that before you look into this Bloch theorem. Otherwise, I'll be taking a quick recap of the free electron theory even before this topic. So first what we'll be discussing is the free electron theory, and then we will see the introduction to Bloch theorem, where we will be discussing what are the situations that led to the development of Bloch theorem, and then we will see the explanation of Bloch theorem and its applications. Now coming to the free electron theory, the free electron theory of solids, which is applicable to all solids, that is both metals and non-metals. This theory aims to explain the structures and the properties of their solids through their electronic structure. Here electronic structure means by understanding how the electrons are situated in a solid. By understanding that, they thought that they could explain the structures and properties of solids. Now, this theory, free electron theory, could successfully explain the electrical, thermal and magnetic properties of solids. So, when it comes to electrical properties, mainly here we talk about conductivity. How do materials conduct? When I'm talking about solids, in that metals if we take, so how do metals conduct depending upon their electronic structure or the movement of the electrons? That is what we are going to discuss in electrical. And thermal means it is related to heat. So with the increase in temperature, what are the changes that are happening in the motion of the electrons? Based on that, we are able to describe the structure and the properties, and also some magnetic properties of solids. And if you come to the free electron theory, we classify it, or it is in three main categories or main stages we have. The first one is the classical free electron theory, which we call it as CFET. C stands for classical free electron theory. And then we have the quantum free electron theory, QFET, quantum free electron theory. And then we have the zone theory or the band theory of solids. So we have discussed these two in detail, but we will quickly have a recap and then we will go to the zone theory today. In free electron model of the metals in solid state physics, whenever we talk about solid state physics, we first consider the free electron model. It represents a metallic solid as a container that is filled with gas composed of electrons. So whenever we are talking about a solid, it is just considered that it is a container, the solid is a container and there are electrons inside the container, and it is just like a container that is filled with gas, and how the molecules of a gas move around inside a container. The same way they assumed that the electrons will be moving freely inside the solid. So the free electrons, considered identical to the outermost or the valence electrons of free atoms, they are presumed to be moving independently of one another. So these electrons, which we are considering them to be inside the container or the solid here, they are moving independently of one another, means nothing, no interaction between the electrons or the other ions is considered. So they are moving freely throughout the entire crystal. Now, what was the problem here is the electrostatic interaction of the detached electrons with the positive ion cores and with other electrons is assumed to be negligible. So this was the drawback here. If you are considering a solid which consists of a number of atoms, so when we have a number of atoms in a solid arranged like this, when the electron comes out, so when you have an electron detached, so what we see here is we will be seeing them as positive ion cores with free electrons. So I may represent it simply like this. So these are the positive ion cores with the electrons that are detached. So now we are going to talk about these electrons. Detached electrons, they are not interacting with the positive ion cores and with the other electrons. Suppose if I talk about the movement of this electron throughout the entire crystal. So obviously this electron may have interaction with this positive ion or with the next electron which is coming in its way. So the same way with all the electrons that are present, because all the electrons are moving inside very freely, so there would definitely be the interactions between the electrons or the electron and the positive ion side. So but here they assumed it to be negligible. Now to this solid, if you are considering a solid like this, actually what they presumed is they are free to move inside and it's like a container where there is no fixed place. They can move anywhere inside. But when an electric field is applied, the free electrons will experience a slow drift motion in the positive direction of the field. Now suppose we apply a electric field to this solid. What happens to the electrons? These electrons will start drifting towards the positive side because of opposite charge. So they will be drifting. There will be a drift motion in the positive direction of the field and produce current. So if they have to explain the electrical properties or the electrical current, they need free electrons, and we all know that current is due to the motion of electrons. So with the help of this assumption, when they said when an electric field is applied and the electrons will drift towards the positive side, means all the electrons are in motion and that constitutes current. That is how they could explain the current or the electrical characteristics in a metal. Now, if you see the success of classical free theory, it proved the validity of Ohm's law. So what does Ohm's law say? As long as the physical state of the conductor remains the same, the ratio of the potential applied to the current is always a constant. So now when they have applied a field, and because of the applied field, there is drift motion in the electrons and there is electric current. And by varying the voltage, if you study the current, variation in current, V upon I is found to be a constant. So it proved the validity of Ohm's law. And it could give a satisfactory explanation to the mechanism of electrical current in conductors and thermal conductivity of metals. So with the help of these movement of electrons, they could successfully explain the mechanism of electrical current, how current flows in a conductor. So when I say here conductor, metals are very good conductors. So when they have taken a metal and applied current, because of the drift motion, there is electric current. So they could also explain the movement. And also they could explain the thermal conductivity. Thermal means, again I tell you, it is related to heat. So whenever there is a heat supplied, these electrons get agitated. And then also there is a motion in electrons, and they could also explain the thermal conductivity. It also explains the optical properties of metals. So some optical properties of metals also could be explained with the help of free electron theory. And then it derives the Wiedemann-Frenz law, which is a very important law which connects both electrical conductivity and thermal conductivity. So all these were the advantages or the successes of the classical free electron theory. Now coming to the failures. What was the failure of this classical free electron theory? Temperature dependence of resistivity could not be established correctly. Temperature dependence here means when the temperature varies, how does the resistivity vary? So because when we talk about resistivity here, if the resistance is more, the conductivity is less. So what happened here is, if you increase the temperature, how does the resistivity vary and how does it affect the conductivity of metals? That is what it could not explain correctly. And also the heat capacity and the paramagnetic susceptibility of the conduction electrons. These conduction electrons, how do they move? So what is their susceptibility in moving in an electric field? That also could not be explained successfully. And also, it could not predict the correct values to the mean free path of electrons. So when I talk about mean free path here, mean free path means the total distance that is traveled by the electrons. Of course, later on we had between the collisions, but here they have neglected the collisions. But what is the mean free path? The total distance, or I say here mean means the average distance that is traveled by the electrons. They could not get the correct values. So all these were the failures of classical free electron theory. So we had the quantum free electron theory. So what does quantum free electron theory say? A conduction electron in a metal experiences constant or zero potential. So when we say constant, for simplification's sake, we consider it to be zero. And the electron is free to move inside the crystal, but it will not come out of the metal because an infinite potential exists at the surface. So according to quantum free electron theory, what we are seeing here is the electron is moving in a constant potential. This is one important assumption they have made. Okay, later on, which they had to rethink about this assumption. But the assumption they made here is the electron, the conduction electron means those electrons which are responsible for conduction in metals. We call them as conduction electrons. They experience a constant or zero potential. Constant potential here we are considering it to be zero. And this electron is free to move inside the crystal. So it can move anywhere inside the solid, but it cannot come out of the metal. It has to be bound. If I'm taking a solid, the electron can move anywhere inside the solid, but it cannot come out of the solid. So what they assumed here is there is an infinite potential at the surface. Only when the electron can overcome that, it can come out. So the electron cannot come out, they said, of the metal because there is an infinite potential which exists at the surface. Now, what are the successes of this quantum free electron theory? So they could very clearly explain the specific heat and magnetic properties which the classical free electron theory failed to explain. And it could also predict the temperature dependence of resistance correctly. So here also the classical theory failed. If the temperature increases, so what happens to the resistivity? If the resistivity decreases, then conductivity increases. This was very well established or clearly explained with the help of quantum free electron theory. Means when we increase the temperature, means when the temperature increases, the resistance decreases. So the conductivity increases. So this they have studied separately for metals and also semiconductors. Okay, so they could establish the relation. How do metals behave with increase in temperature? And then later on, how semiconductors behave with increase in temperature. And it could also explain the thermionic emission of metals. What is thermionic emission? Thermionic again is related to heat. Whenever we say thermal, it is related to heat. So when you take a metal and heat it, so there is thermionic emission. Thermionic emission is nothing but the emission of electrons. As such, the electrons are bound, they cannot be emitted. But when there is an increase in temperature, when you supply heat to which it can withstand, then there will be emission. So that we call it as thermal emission or thermionic emission in metals. Now, what is the failure of quantum free electron theory? It failed to explain some simple questions like why some materials behave like good conductors. Because when they could explain the thermionic emission, they could also explain the thermal conductivity, temperature dependence. Then all materials which have free electrons should conduct. Now, all should exhibit the property of conductivity and they should behave like good conductors. But they could not explain why some materials are good conductors and why some materials are good insulators. Insulators are those which do not conduct. No, when they have free electrons, why they are behaving like insulators? That is a question this quantum free electron theory could not explain. Then there are also some materials which are semiconductors. Semiconductors here means whose conductivity lies in between conductors and insulators. Conductors are highly conducting, insulators are not conducting, but semiconductors lie in between conductors and insulators. So they could explain the other theories but fail to explain why some materials are good conductors, some are insulators and some are semiconductors. Basically, it failed to explain the classification of materials. So when we see materials in nature, so some are ready to conduct the heat or electricity, we call them as good conductors, and some are bad conductors, which we call them as insulators. Some are partially conducting, we call them as semiconductors. So that major classification which is there could not be explained with the help of quantum free electron theory. Now, this failure, the failure of the quantum free electron theory to explain the classification of materials led to rethink about the basic assumption. So they had a basic assumption, I told you, in quantum free electron theory. What was the basic assumption? The potential inside the crystal is constant. That is the assumption they made. But with this assumption, they are not able to explain this classification. Then they started thinking, no, for all those who are working on projects or doing some research, this is the way you need to think when you are trying or when you are stuck up with something. So just go back and see what were the assumptions that were made, what are the successes, what are the failures, and where we need to reconsider or look into the assumptions we have made or make some changes in that. So this is the thought that came to this scientist. What they said is the potential inside the crystal really constant? They started thinking. Then later on, they realized that this is an oversimplified assumption. Oversimplified means for simplicity's sake, they have taken that the electron is moving inside a crystal which has constant potential and let the potential be zero. That is what they have considered. But that is an oversimplified assumption that the electrons move in a constant potential or zero potential is not the actual picture. When they have realized that, then they started again experimenting and finding out what could be the case. If the potential is not constant, how does it vary? So now let us look into why the potential inside the crystal is not constant. No, the oversimplified assumption proved to be wrong. So there should be some potential inside which is varying. So why the potential inside the crystal is not constant? Now we see a crystalline solid. Now, whenever you take a solid, it consists of a lattice which is composed of a large number of ionic cores at regular intervals. And the conduction electrons move throughout the crystal. So here, if you see here, this is the crystal lattice. Crystal lattice here means a regular arrangement of atoms. We call as a crystal lattice. But in a crystal lattice, when the electrons are made free, if you are removing the electrons, then what happens? You are left with positive ion cores. That is why we are showing the positive ion cores, and they are spaced at regular intervals. They are equally spaced. No? So we are considering, if you consider this regular spacing of the positive ion cores and the free electrons, these free electrons move throughout the crystal. So that is what is considered. Now these electrons move in a periodic potential of the positive ions. So this new term is coming. They said it is periodic. Periodic means, when I say periodic, anything that repeats at regular intervals of time. Regular intervals of time or space. Now we call it as periodic. Now here, electrons move in the periodic potential, they say. So the assumption that they are moving in a constant potential is not helping them to prove certain things or to explain certain classification of materials. So they started considering that the potential should be periodic. So how do we explain this periodicity? So the periodicity arises due to the periodic arrangement of positive ions in the lattice. So I explained, this is the periodic arrangement you can see in the crystal. So when an electron approaches a positive ion, there will be attraction between the two and the potential decreases. So if you are talking about an electron, one electron we consider. So if this is moving in this direction, and when it approaches a positive ion, okay, so when it approaches a positive ion, there will be an attraction because they are opposite in charge. There will definitely be an attraction, which we call it as the electrostatic force of attraction. There will be an attraction and the potential decreases. So what they have considered is, so as the electron comes from one positive ion side to the other side, its potential varies. How it is varying? It is decreasing at the positive ion side. So when it is coming here, again it decreases. Again if it comes here, decreases. But what is it in between two ions, where there is a minimum attraction between the positive ions and the electrons. So the potential is minimum at positive ion sides, but it is maximum in between two ions. So when we are taking the positive ions at the positive ion sides, the potential is minimum. But between any two positive ions, in which direction the electron is moving, the potential is maximum. So this is what we are talking about is periodicity. If you see here in this diagram, I say this is a positive ion side. These are the positive ion sides, or we call them as nuclei. Okay. Now an electron which is approaching this positive ion side, if we are plotting, x is the distance versus potential. Okay. And we have considered that at the surface the potential is maximum or infinite. Now if an electron approaches a positive ion side, the potential is minimum. So at this side it is minimum. Now when it moves away from this positive ion side, and between these two, the potential is maximum. So what is happening to the potential? It is becoming maximum. So if you see at the positive ion sides, these are the positive ion sides. So at the positive ion sides, the potential is minimum. These are the minimum points exactly at the positive ion sites. And in between the positive ion sites, these are maximum. So what you see here is their periodicity. The potential is varying periodically. How? At the positive ion sites it is minima, again maxima, minima, maximum, minimum, maximum, and so on. And as the number of atoms increases, you can see the same periodicity throughout the lattice. So the concept of varying potential inside the crystal due to the presence of positive ions is introduced. So now this new concept of varying potential is introduced. We have also understood why the potential is varying, because the electron is moving in a periodic lattice of positive ion cores, and because of the interactions between the electrons and the positive ion sites, the potential is becoming minimum at the positive ion sites, and in between two positive ion sites it is maximum. So there exists a periodicity. So we say that the potential is varying periodically. Now coming to the Bloch theorem. In order to solve this, a scientist by name Bloch in the year 1928, so what he gave a theorem which applies to the wave functions of electrons. So when we are talking about electrons, we have discussed this concept in detail in our module 1. Now when we are talking about electrons, electrons are particles, but they exhibit dual nature. Means they behave as particles sometimes, but they also exhibit nature. Moving electrons are considered to exhibit wave nature, and in order to show the wave nature, we need a wave function. So what he did is, he applied this wave function applies to the wave function. This Bloch theorem is applied to the wave function of electrons inside a crystal. And it rests on the fact that the Coulomb potential inside a crystalline solid is periodic. So he started with this concept that the potential is not constant and it is periodic. So when it is periodic, how do we show or how do we incorporate this periodicity into the wave function which we are using to represent the wave nature of electron? Because it is the electron that is moving, so it exhibits wave nature. So when it is exhibiting wave nature and because its potential is periodic, how do we incorporate this? So he is resting on this concept of Coulomb potential, we call it as, which is periodic. So as a consequence, the potential energy function. So whenever we denote the potential, we are denoting it as V as a function of X. How it varies with X, that is the position we are going to see. So as a consequence, the potential energy function in the Schrodinger's equation should be of the form V of X is equal to V of X plus A. Because how we are getting this wave function, we have already discussed the Schrodinger wave equation. What was the Schrodinger wave equation we have seen? Dou square psi by dou x square plus 2m into E minus V upon h cross square into psi is equal to 0. So here we have considered only V, but now how does this V vary in a lattice? When we are considering the periodicity of potential. So he said this has to be included in the Schrodinger equation because the solution of this gives the wave function. The solution of the Schrodinger equation gives us the wave function. So whenever we talk about the wave function, we also have to talk about the periodicity. So what is the periodicity here is, it depends upon A. A represents the lattice parameter. Lattice parameter here is when we are talking about the positive ion sites. If you imagine that these positive ions are separated by a distance A, and I said they are periodic. No, between any two positive ions you take, the distance is A. So we will call it as the lattice parameter. So whatever the potential at this point is, it will be the same after a distance A. So that is the meaning. V at x is equal to V, that is the potential, at x plus A, where A is the lattice parameter. Now, Bloch theorem establishes the wave function psi k of R in a crystal that is obtained from the Schrodinger wave equation, and it can be expressed as a function of or a product of the plane wave and a function of UKR. Okay, so which has the same periodicity as the lattice. What it means here is, if you are taking the wave function psi k of R, you are expressing it as a product of EIKR, we call it as iota KR, which represents a plane wave. Even if you take in classical physics, you have a plane wave, a wave function represented by a plane wave. Now, how do we represent to incorporate this periodicity? We are introducing a periodic function, okay, which is UK of R, which describes the periodicity. So now we are trying to write the wave function psi k of R. So why I am calling is k is a wave vector here. So E is represented as UK of R into EIKR. So this represents the plane wave and this represents the periodicity. So the Schrodinger equation can be expressed as a product of the plane wave and a function UKR. And this is having the same periodicity as the lattice. Whatever the lattice periodicity we take, that is the distance between any two ions or the lattice parameter. So the same periodicity applies to this wave function also. Now this Bloch theorem, in essence, it formulates the condition that all solutions psi of R for any periodic potential V of R, they have to meet the condition psi k of R is equal to UKR e power IKR. So we started with the wave function and now we are trying to apply it to the potential. So what they said, all these wave functions, they have to satisfy this condition because they are arranged in a periodic manner, the positive ions, and then they are experiencing periodic potential. So they should obey this condition. Psi k of R is equal to UK of R e power IKR. So where k is the allowed wave vector for the electron and that is obtained from the constant potential. We are talking in terms of k now. Now U of R is a wave function with the periodicity of the lattice. So what we are talking about again here is the periodicity. So when you have to represent UKR should be equal to UK of R plus A, where A is again the lattice parameter. So we are first talking about the wave function, which is expressed as a product of function, which is talking about periodicity, and then a plane wave. Now, how do we modify this periodicity? How is it periodic? To explain the periodicity, we are writing UK of R is equal to UK of R plus A. So any wave function meeting this requirement will be called a Bloch wave. So this condition, if a wave is satisfying, you will call it as a Bloch wave. Now what does the statement of Bloch theorem say? So for electrons in a perfect crystal, there is a basis of wave function with the properties. What are the properties? Each of these wave functions is an energy eigenstate. So now we are talking about the wave function and then we are relating it to the energy eigenstates. So the energy values represents the eigenstate. Then each of these wave functions now is a Bloch state. And meaning that the wave function psi can be written in the form of psi k of R, UKR, e power IKR. And it has the same periodicity as the atomic structure of the crystal. So UK of R is equal to UK of R plus A. So what if you are looking at the Bloch theorem, what is the essence of the Bloch theorem? What we are seeing is, so the wave function is represented as an eigenstate, is an energy eigenstate, and the wave function is a Bloch state because they are following the periodicity and they are satisfying the two conditions. So we have put both the conditions here. Now we are applying the potential. So the potential is varying as V of x is equal to V of x plus a, where a is the lattice parameter. And this is the solution. If you are considering the solution to this Schrodinger wave equation, so the one-dimensional Schrodinger wave equation is given by psi k of x is equal to uk of x e power ikx. So now you see, we were talking about uk of r, and now we want to represent it in terms of uk of x, because whenever we are talking about a wave function, actually crystals are in 3 dimension. Whenever I am talking about a crystal, it is a 3-dimension one. So the Bloch function in 3 dimensions, we represent it as psi k of r is equal to uk of r e power ikr. Okay, so this is how we represent the Bloch function in 3 dimension. In free electron theory, the wave function is represented by e power ikx in 1 dimension. So whenever I'm talking about, when we are deriving this expression now, we will be doing it in 1 dimension. 1 dimension means here I'm talking only the arrangement of atoms along the x-axis. Okay, you will have it along y and z also, but to explain, we are considering only along the x-axis. So we are talking only in terms of 1 dimension. So when I represent the wave function, I will represent it in terms of x and not r. So for 3 dimension. So if I have to represent it in the y direction, I may use e power iky. If I have to represent along the z, I may use e power ikz. So here, I hope this point is clear. We are limiting ourselves to 1 dimension. So we are writing it as e power ikx. So the Bloch functions represent the free electron wave that is modified by the periodic function uk of x in 1 dimension and uk of r in 3 dimension. This also you have to be clear. So we will be modifying the wave function with the help of ukx in 1 dimension, and we will use uk of r in 3 dimension. Now the periodicity of ukx is in accordance with the periodicity of the lattice. Okay, so how this periodicity depends? It all depends upon the periodicity of the lattice, means how the atoms are arranged in that particular crystal. Now we will consider, let there be n atoms in a linear chain of length L. So what we consider here, I told you, we are considering only the arrangement of atoms along the positive direction, that is the x-axis. Okay, so there are like this, there are n number of atoms. So it will continue. There may be many atoms. So the distance between each is a, and they are periodic because we have considered it is periodic. Between any 2 atoms you take, this is a. Okay, now uk of x is equal to uk of x plus na. So we have considered uk of x is equal to uk of x plus na. Initially for 1, we have considered x plus a. Now if you are extending it to n atoms of linear chain L, so in a length L, if I am considering these are n number of atoms. What are the number of atoms here? N atoms are arranged in a length L. So how do I get the length L? N multiplied by A. So L can be obtained by multiplying the number of atoms and the interspacing between them. So L is equal to Na. So this gives us the space. So if I want the space between the first and the second, A. First and the third one, this will be 2A. So this will be 3A. 4A and so on. From the first to the last, the distance will be Na. So that is why we are writing uk of x plus Na, extending it to the entire crystal. Now psi k of x plus Na will be equal to what? Wherever we have x, we will be replacing it with x plus Na, because we want to extend it to the entire crystal. So let us take the expression psi k of x is equal to uk of x into e power ik of x. Okay, so here this is what we have taken initially. Now we are replacing each x with x plus na. So uk of x plus na will be equal to uk of x plus na and e power ik of x plus na. And now what we have considered here, the periodicity at x is the same even if you extend it to na. So uk of x plus na. So I can write for this uk of x plus na as uk of x. This is from equation 5. We are writing it as uk of x. And now we can expand this term e power ik of x plus na. E power a plus b will be e power a into e power b. So I am writing this as e power ikx into e power ik na. So I can write this simply as e power ikx into e power ik na. So where I am using the formula e power a b can be written as e power a into e power. Okay. So once you get this, what is uk of x e power ikx? uk of x e power ikx is nothing but psi kx, the function we have taken. So the wave function, it represents the wave function at x. So psi k of x, and then we are left with e power ikna. So psi k of x plus na is equal to psi k of x e power ikna. So let us take this as equation 6. So what we have taken? We have taken the wave function and we have considered n atoms arranged in a linear chain of length L because we are limiting ourselves to one dimension, and we have substituted in place of x, we have extended it to all the n atoms with the lattice parameter a. So we have substituted x plus na and we have simply solved it, simplified the expression. So we are getting psi k of x plus na is equal to psi k of x e power ik of na. Now, let us take the complex conjugate. Why we need to take the complex conjugate? As such, if you see the wave function, it does not have any physical significance, and using it you cannot locate. If you have to know the probability of finding the particle or the electron anywhere, you need to normalize it. That is, you have to multiply it with a complex conjugate. So what is the complex conjugate of psi k of x plus na will be psi k star x plus na. So psi k star x plus na will be equal to what? Psi k star x into e power minus ikna. So the complex conjugate of e power ikna will be e power minus ikna. So in equation 6, what we had? Psi k of x plus na is equal to psi k of x into e power ikna. And this is equation 6. Now we are going to take the product of 6 and 7. Means you are going to multiply psi k of x plus na into psi k star of x plus na. Means we are multiplying this function with its complex conjugate. So what will be the left hand side? Psi k of x plus na into psi k star of x plus na. This should be equal to, on the right hand side we have psi k of x, psi k star of x. What happened to this? E power ikna into e power minus ikna. So we will now take the reverse. E power a into e power b will be equal to e power a plus b. So I can write it as e power ikna minus ikna. So these two will get cancelled. So you will have e power 0. So this should be equal to 1. So what we are left with is, because these two terms e power ikna into e power minus ikna, after taking the product, when you multiply, you are getting it as 1. So psi k of x plus na into psi star of x plus na, multiplying it with its complex conjugate, is giving us psi k of x into psi k star x. So what does this equation mean? The probability of finding the electron is the same in the whole lattice. Means what? Whatever the probability is of finding it at x, is the same as finding it at x plus Na. So if you are, because you see the equation, so whatever the probability at x is, it will be the same as x plus Na. So the probability of finding the particle or the electron is the same in the whole lattice. If you are taking the entire lattice, the probability remains the same. Now, if you consider this Bloch function, and if you are substituting, because we have taken the result e power ikna is equal to 1. So, when will be the values of e power ikna be equal to 1? Only when kna is equal to 2 pi n, where n takes on the value 0, plus or minus 1, plus or minus 2, and so on. So, from this, what we can derive here is, because kna is equal to 2 pi n, so k can be written as 2 pi n upon na. So we will simply transpose it. You get 2 pi n by na. And na is nothing but, it gives us the total length of the crystal. So we are trying to represent the wave vector k in terms of the length of the crystal, that is 2 pi n upon n. So what we try to understand here is, when n is very large, means whenever you consider a crystal, it consists of n number of atoms, and the number of atoms are very large. Depending upon the atomic number, you know how the size of the crystal lattice increases. If it increases, the number of atoms are more, that means. So when we consider a crystal with a large number of atoms, the allowed values of k become closer and closer. So as the value of n increases, keeps on increasing, what happens? These values of k, they become closer and closer. So then what happens? Along the k-axis, it becomes quasi-continuous. So what we are trying to understand is to explain both when it is small, what happens, and as it becomes large, how the values of k come closer and closer, and it looks as though it is a quasi-continuous state. Now, what is the conclusion of this Bloch theorem? So, it tells us about the periodicity of the potential. So, the first thing we understood is the potential periodicity, how the potential varies periodically, and this Bloch theorem clearly explains that, and this periodicity can be applied to classify the materials into conductors, insulators, and semiconductors. You see, because of the oversimplified assumption that the electron moves in a constant potential, they could not explain the classification. Now, by considering the periodicity of the potential, this classification into conductors, insulators, and semiconductors could be very well explained. So, this forms a basis for the band theory of solids. So, that is why Bloch theorem has got a lot of importance, because it forms a base for band theory. Now, Bloch waves are very important in solid state physics because they often are used to describe an electron in the crystal. If you have to describe an electron, if you have to show how an electron is, how it moves, you need the Bloch waves. Okay, and also this we have discussed, they represent the eigenstates and they can be represented in terms of Bloch waves. So this is one more advantage of Bloch theorem, and also we have seen that this fact underlies the concept of electronic band structure. So basing on this, we are going to divide them into bands, and based on this, we are going to explain many electrical properties and how they are behaving as conductors, semiconductors, and insulators. And the application of this Bloch theorem is to classify the materials electrically, and this was done by Kronig and Penny. Okay, and it is known as the Kronig-Penny model, which we will be discussing in our next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.